Okay, so last time we learned the definition of matrix Lie group. So matrix Lie group is a closed subgroup of the general linear group. So and we learned general linear group over C and over R, and special linear group, and what else? Orthogonal group, unitary group, special unitary group, special orthogonal group, and symplectic group over C and over R, and compact symplectic group. Have you learned something else? Yeah, something like that. And today we will continue with some topological properties. A matrix Lie group G is connected if for all elements A and B in the group there is a continuous path A of t. T is from A to B, say, with connecting the two elements. So A of the initial point is the first element, and the final point is the second element. Okay. In fact, this definition, if you are usually under this condition, is called path connected. But for matrix Lie group, it turns out that it's in fact a manifold. So path connected and connected, they are equivalent. So it's safe to say that the definition of connectedness is this. Usually, this kind of definition refers to a path connected, but they are equivalent for this. And the identity component of G. So this means is denoted G sub 0, and which means, in other words, G sub 0 is the connected component of G containing the identity element. Now, because now we can talk about whether a subset is connected or not using this definition. Connected component. So every group or every matrix Lie group will be decomposed into connected components, and just look at the connected component containing the identity element. That's called the identity component, and denoted by G sub 0. And property of G sub 0 is as follows. So G sub 0 is a subgroup of G, and not only just a subgroup, it's a normal subgroup of G. The G0, the identity component itself, becomes a matrix Lie group or subgroup, and it's a normal. The proof is not difficult, and it's interesting. So read the textbook, or you can prove it yourself, I think, if you think about it. So you can just show that it's subgroup using this definition. It's closed under the multiplication, the operation, and then you can show that if A is in G0 and B is in G, then you can show that A, B, B inverse is in G0. So it's in fact a normal subgroup. Okay. Right. Proposition GLN C, SLN C, and also for R, UN, a special unitary group, SON for n greater than or equal to 1. They are all connected. These are connected. So these are connected Lie, matrix Lie groups. Again, proof is not difficult, so just read the textbook. Now we need to introduce one more topological definition. Matrix Lie group G is simply connected if, first of all, it is connected and every loop in G can be contracted to a point. Contracted to a point. So it's a usual definition in topology. So for example, contract to a point means, loop means a path starting and ending at the same point. This can be contracted to a point like that by moving this inside, something like that. So for example, the disk is simply connected, but this ring is not simply connected. This is not simply connected. Because no matter which loop you have here, you can always contract to a point inside this space. But here, if you have this loop, you cannot contract to a point inside this space. So it's a typical example of a space that's not simply connected. And interesting examples are the following two proposition. Let's use the next page. SU2, the special unitary group, this is simply connected. Proof. From exercise 2, which is one of the homework problems, exercise 2 says that SU2 is homomorphic to S3. The sphere, three-dimensional sphere, and it's known that S3 is simply connected. This is a topological fact. So because this is topological sense the same as S3, and it is known to be simply connected, so yes, it is simply connected. And in fact, the fact is that SUN is simply connected for all n. Another fact, SO3, a special orthogonal group, this is homomorphic to RP3, the real projective space. And it is known that this space is not simply connected. So you can, if you are interested, you can read the textbook, proposition 1.17. And here, RPN is the real projective space. and which means you can think of this as lines, set of lines through origin. Through the origin in Rn. So in R2, for R2, all the lines are elements. Just line itself is an element. Oh, actually, it should be R plus 1, because the dimension is decreased by 1. So this means the dimension of this space. So it should be R plus 1. So this is something like a circle, unit circle, but these antipode points are identified because a line through origin passes through these 2 points, and we have to consider this as just one single point. So you can think of this should be RP1. Right? This is RP1. So RP1 is basically a circle with antipode points identified. And RP2 is the sphere with antipode points are identified, etc. Okay, and let's move on to the next section. And homomorphism. Yeah, so homomorphisms are a very important concept. So G, H say that they are matrix Lie groups. And phi is a group homomorphism. Group homomorphism means as it preserves the multiplication structure. G1, G2 is equal to G1, G2. And okay, let's try it in this way. So this is just group homomorphism, but we want to talk about Lie group homomorphism. Is a Lie group homomorphism is a Lie group homomorphism if it is a group homomorphism. First of all, like this, and it is continuous. So continuous group homomorphism. Okay, so group homomorphism with continuous. In fact, it's really difficult to find group homomorphism which is not continuous. So mostly, if you have any reasonable group homomorphism of between Lie groups, there will be a continuous function, but the definition is like this. And if, as usual, if in addition, phi is 1-to-1 and onto, and phi inverse is also continuous, then we say that phi is a Lie group isomorphism. Okay. And whenever there is a Lie group isomorphism between two matrix Lie groups, we say that they are isomorphic. So if there is a Lie group isomorphism, phi from H to G to H, we say that G and H are isomorphic and denoted G isomorphic to H. So homomorphisms give us a way to relate two different matrix Lie groups. A simple but interesting example of a Lie group homomorphism is the determinant function. The determinant from GL and C, so this is a matrix Lie group. So whenever we have an element here, it's a matrix, so we can compute the determinant. So the determinant is element in the field, so it's going to be in the field. But GLN is a set of invertible matrices, so it's in the determinant is non-zero, so it's C star. C star means C minus 0. Where we have, whenever we have a matrix here, we assign this value to it. Of course, this is a continuous function. And it's a group homomorphism because determinant of A, we all know that the determinant of A is equal to determinant AB is equal to A times determinant of B. So this means group homomorphism, and it's a continuous, so it's a Lie group homomorphism. All right? And there is a very interesting Lie group homomorphism. There is a Lie group homomorphism, say phi from SU2 to SO3, such that phi is 2 to 1. It's not 1 to 1, but 2 to 1 and on 2. With the kernel being identity and plus or minus identity. Okay. So these two are very similar, almost the same, except this is in some sense double of this. We have two copies of this related in some way. Proof is in the textbook, so I'll just refer you to the textbook. But it's a little long, but it's interesting. So it'll be great if you can read the textbook. And let's see some consequences of this. I mentioned that SU2 is homomorphic to S3, the sphere. And by the proposition, S or 3, this is isomorphic to this, quotient by the kernel. But the kernel is like I and minus I, so this is S3, isomorphic to S3 with I and I minus I identified. And similarly for X and minus X. So it's quotient by the relation where X and minus X are identified. So this is like S3 with antipodes are identified. Antipode points are identified. So this is exactly what I mentioned earlier for for sphere case. So for two-dimensional case, antipode points are like this. Antipodes means X and minus X. These are the ambient space. So these two are identified, these two are identified. And this is really, what this really is RP3. Okay, this is or this is line in R to the fourth, and this is the same as this. And this is another way to see that SO3. So this is another way to see that this is homeomorphic to RP3. Okay. So this one is simply connected, but this is not. Any questions so far? Okay. And the next section, maybe I can use somewhere below this. Section 1.5. But I think this section is short enough so that I can fit it inside in this space. Lie groups. Yeah, finally, Lie groups. We only talked about matrix Lie groups. Now it's time to talk a little bit about matrix, just the Lie group. A Lie group, by definition, is a smooth manifold, say G, which is also a group, and such that when we have a group, we have two operations, multiplication and inverse. So we have this multiplication operation, so G H maps to G dot H. This is the multiplication in the group. And also this inverse map, G maps to G inverse. These two maps are smooth, such that these are smooth maps. Then this is called a Lie group. So it has algebraic structure and geometric structure at the same time. And the fact is, so these matrix Lie groups, the set of matrix Lie groups, this class, if G is a matrix Lie group, it is a Lie group. So Lie groups, but the converse is not true. This is a proper subset. There is a Lie group which is not a matrix Lie group. But like I said last time, most matrix Lie groups, most Lie groups which are interesting are indeed matrix Lie groups. So we will just restrict ourselves to only matrix Lie groups. So, for example, G R cross S1. This is the circle. And we define the multiplication in this way. X1, Y1, Z1, X2, Y2, Z2 is defined to be X1 plus X2, Y1 plus Y2, and e to the IX1, Y2, Z1, Z2, something like that. Then you can show that this is indeed a group. You can see that it satisfies all the axioms for a group. And the smooth is easy to see, smoothness of these two maps is easy to see. So this is a matrix Lie group. Lie group. But it turns out that it's not a matrix Lie group. But as you can see, the multiplication is defined a little strange, in a strange way. So, yeah, we will not be interested in Lie groups like this. We will only be interested in matrix Lie groups. Okay. Yeah, that's about the first chapter. Now, second chapter is the matrix exponential. So the first section. The exponent of a matrix. In this section, we will learn how to define the exponential of a matrix. The definition is, in fact, quite simple. If you know the power series for real exponent, so X is a square matrix, and the exponential of X is denoted e to the x or exp of x. This is just a sum like this. So this is exactly the same as the definition of an exponential of a complex number. And this is defined for every matrix n by n because it always converges. This series always converges. A series, this for e to the x, this one converges for all x. And moreover, it is a continuous function. Okay. We can, because this can be thought of as c to the n squared. And for a matrix in that set, we can define the norm of x is defined the usual way. So it denoted like this. Norm of x is exactly the norm in this space. So it's square root of summation of all the entries, the square root of all the entries. So j k equals 1 to n, xij it should be like this. Yeah, in this textbook, the author tries to avoid the usage of I because, you know, as you can, I is the complex number. So, and equivalently, this is the same as trace x adjoint and x. They are the same. You can just check this. It's very simple. And using this definition, you can see that a sequence of matrices approaching to x can be expressed in this way. This means the norm of x minus xm is 0. The limit of this norm approaches 0. Yeah, like last time and today's lecture, and unfortunately a little more times in the future, we will just see many definitions and properties listed like this without any proofs. So it might be a little boring, but these are very important because we will be using this. So try to remember the definition and propositions. X, Y, these are n by n matrices. First, e to the 0 is the identity matrix. E to the x adjoint is e to the x adjoint. 3. This is always invertible. And the inverse is like that. So try to see the similarities between the exponential of matrices and the exponential of the usual complex numbers. They are very similar, but not exactly the same. For complex numbers, alpha and beta, we can separate this like a usual exponential row for all alpha beta in the complex number. 5. If xy commute like this, then e to the x plus y equals e to the x times e to the y, and of course e to the y, e to the x. 6. If C is an invertible matrix, then e to the cx C inverse is equal to C e to the x C inverse. Okay, so 1, 2, 3, 4, they are pretty simple. 6, this, if you consider the definition of the exponential, this follows very easily. 5 is something that's a little different from the usual exponential. So because this condition is important. If we don't have this condition, this may not be true. So in general, you cannot just separate the exponential like this. This is not true in general, unless x and y is equal to y, x times y equals y times c. For matrices, this is not true in general, right? So without this, you cannot say that. Okay? Notice that 4 is a special case of 5 because these two always commute. Okay? All right. Next proposition, X is n by n matrix. Then e to the t times x for real number, complex number, but usually we consider t as a real number. This is, we are considering this as a curve, so it's a real number. Smooth curve in the whole space, and so this is a function as a it's a function of t real number. Okay? So if you want, you can like that, t real number. And we have some derivative rule, tx. Because this is a function in one variable, we can talk about the derivative, the usual sense. And this is equal to x times e to the tx, and also equal to e to the tx x. So it looks like it just follows the usual derivative rule, the chain rule, right? It's exactly like we apply the chain rule. So that will be helpful to remember this. And therefore, if you take the derivative and set t equals 0, this becomes e to the 0, which is the identity, so it's going to be x. This will be used later. So used many times, I don't know. Many times. Will be used many times later. Oh, and one thing to notice is that d dt, this follows the usual derivative rule, but if you have x plus ty for two matrices x and y, this is not true in general, e to the x ty times y. This is true when we have only one term like that, without any constant matrix. Okay. So now that we learned the definition of the exponential, the next question would be, how can we compute such a exponential? But this is in fact, I think you learned this in linear algebra, undergraduate linear algebra course. But let's review that anyway. Computing the exponential. First, simple case is that is the following. Suppose that x, which is an n by n matrix, has n linearly independent eigenvectors v1 dot 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 vn with eigenvalues lambda 1 dot 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 lambda n. This means x is diagonalizable. So this means x can be written in this way: C D C inverse, where C is some invertible matrix, D is a diagonal matrix whose diagonal entries are like this, the eigenvalue. So having n linearly independent vectors, eigenvectors, is equivalent to having an expression like this. Okay, in this case, the exponential is easy because exponential is C, D, C inverse, but the previous proposition told us that C e to the d, this is equal to C inverse. And what is this? This one is like exponential of each entry. If you just follow the definition, you can easily see that this is e to the lambda 1. Because if you take the kth power here, that's nothing but having kth powers for each entry there, for a diagonal matrix. So it just becomes diagonal matrix whose entries are e to the lambda 1 dot 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 e to the lambda n. This is the usual exponential of a complex number, C inverse. So now we just multiplying these three matrices, which we can do easily. So it's possible to compute the exponential. but not every matrix is diagonalizable, so we have to deal with the other case. And before doing that, let's see what happens if X is nilpotent. If X is nilpotent, then this means X to the K equals 0 for some integer K. If X is nilpotent, then what is e to the X? This is in fact just a polynomial. This is a polynomial. I plus X squared over 2x cubed over 3 factorial dot dot dot. All you need to do is to compute up to k minus 1, because the other one, the remaining one, will be 0. So it's just a polynomial, so we can compute this. And the fact is, this is a well-known fact in linear algebra. I think you have heard of this before. Every matrix X can be written uniquely as X equals S plus N, where S is diagonalizable, like this, and N is nilpotent. Oh yeah, one more. And Sn equals Ns. So they commute, these two matrices commute each other. Using this fact, you can compute e to the x for every x. Because, let me write down right there. In this case, then, what is e to the x? E to the s plus n. But because they commute, we can separate e to the x and e to the n. But this is a diagonal matrix, so we know how to compute that. This is a nilpotent matrix. We know how to compute that. So that's a polynomial. So we can compute the product of these two. So that will give us a way to compute this for any matrix X. So if you have enough time, then you can compute this. But of course, I think it takes a lot of time. But it's possible. Okay, so we learned the exponential of a matrix. So the next will be what? What will be the next one? Yes, logarithm, the inverse of the exponential. We want to talk about the inverse. Computing the, oh no, I was writing the previous section. This has been done. So 2.3, the matrix logarithm. So like this. But what does this mean? Just consider a real or complex case, or just say complex case. What does this mean? What does this mean? This means x equals e to the y, right? So so y is the value satisfying this. But the problem is there are many values of y satisfying this. So usually there is no just a single valued function continuous defined for a whole complex space. So usually we have to consider like branch cut or we have to restrict the domain, etc. So one way to define the logarithm is as follows. using the power series as before. So z is complex number. Let's review the complex number first. And log of z is equal to m from 1 to infinity minus 1 to m plus 1 z minus 1 to the m over m. If you define log z as this power series, then this is holomorphic in this domain. Z minus 1 is less than or equal to 1. So it's close enough to the number 1, then this is well defined and converges and holomorphic, complex differentiable. And of course, if z is in this domain, it is the correct inverse of the exponential, meaning e to the log of z equals z. And if u is less than, the absolute value of u is less than or equal to log of 2, then log e to the u equals u. So they are inverses of each other, like that. Yeah, they have a little different conditions, but under certain, if z is close to 1 and u is small enough, then log is well defined and they are inverses of each other, like that. You cannot define log for the whole space, but for a certain space, for certain domain, then it works just fine, as we expect. So our goal is to extend this definition to the matrix case. The definition is, in fact, exactly the same as this. It works exactly the same way. For a matrix A, define the logarithm of A to be the power series like this. A minus. So if you want to know what it looks like this. Minus A minus I squared over 2 plus minus dot dot dot. It goes like that. Whenever it converges. If it converges, it's defined. Otherwise, it's not defined. And notice that if A is close to the identity, meaning this is less than 1, then log A is well defined or defined. Because each term, the absolute value is less than 1, so this is well defined. Yeah, just like the complex number case. But for complex number case, if this is bigger than 1, this does not converge. But for the matrix case, even if this is bigger than 1, we may have convergent sequence. Even if this is very large, log of A may be defined. When is that? It could be, what's that? Nilpotent. If a minus I is nilpotent, then it's just a polynomial. Polynomial is defined always. It's polynomial. So of course it converges. The theorem is that if, I already mentioned, if A is close to the identity in this way, then log of A is well defined and continuous. As a function, is continuous. And if in this condition this log of A is the inverse of the exponential, like this. And as before, if x is, the norm of x is less than log of 2, log of e to the x is equal to x. So under certain conditions, we can talk about the logarithm, and it is in the inverse of the exponential. Okay. And recall that for complex case, if z is in C star, it's non-zero complex number, then there is a complex number x such that e to the x equals z. So z can be written as the exponential of certain complex number, as long as z is non-zero. We have a similar property for matrix exponential. So this means invertible. It corresponds to invertible. So if, say, A is in GLN, invertible matrix, then there is X, just any matrix or some matrix, such that A is equal to e to the x. So A can be written as the exponential of certain matrix if A is invertible. It's a nice fact to know. Okay. Now, the next section is about some more properties of exponential. I told you that this is not equal to e to the x, e to the y in general. But we can still say something about this. And this is the theorem called Lie product formula. For all x and y, if x and y are just complex n by n matrices, then e to the x plus y equals limit m approaches infinity, e to the x over m, e to the x over y, m, y over m to the mth power. Yeah, this will be used later to see the connection between Lie algebras and Lie groups. We know that this is true if x, y commute. If x, y commute, what happens? This is always e to the x, e to the y. Okay, you can just treat them as just the usual complex exponential. So then this is part is just e to the x times e to the y. If x, y commute, but otherwise, it's not true in general. But if you take the limit, it becomes this. Okay, and another interesting theorem is that, again, X is a complex n by n matrix. Then determinant of e to the x is equal to e to the trace of x. Very simple. Yeah, let's see a proof. If x is diagonalizable with eigenvalues lambda 1 dot 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 lambda n, let's see what happens. Then e to the x is also diagonalizable with eigenvalues e to the lambda 1, e to the lambda n. We know that already. So then what is the determinant of e to the x then? If we know the eigenvalues, all the eigenvalues, then the determinant will be just the product of them. So it's e to the lambda 1 dot 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 e to the lambda n. But now these are just complex numbers, so they can be written in this way, and this is of course the trace. E to the so trace is the sum of the eigenvalues, so it's trace. So for diagonalizable case is diagonalizable case is easy. What about the other case? X is not diagonalizable. If x is not diagonalizable, in this case, we can find diagonalizable matrices xm. A sequence of these diagonalizable matrices approaching to x. This is a homework problem, so we'll do that. And now it's simple. So determinant of e to the xm. Now this is a diagonal matrix, a diagonalizable matrix. So we know that this is equal to e to the trace of x to the m, because xm, every xm is diagonalizable. And because xm approaches x, this means entry-wise, this entry approaches this entry for every ij entry. So this will approach to determinant of e to the x, because determinant is just a polynomial in the entries. And of course, this also approaches e to the trace of x. Okay? And they are equal, so they have to be equal. So that's the proof. Nice and simple fact. All right, and one more interesting property. A function a from the real number to gln is called a one parameter subgroup of GL and C if the following three conditions hold. A is continuous, 2, A0 equals the identity, 3, AT plus S equals AT AS for all TS in the real numbers. One parameter subgroup. Yeah, so this real number is by this map embedded inside this matrix Lie group, and it is a subgroup, and it is it has only one parameter t, so that's why it's called one parameter subgroup. And if you look at this carefully, you can see that actually 2 is not necessary because it follows from 3. If you set t equals s equals 0, then you can check that A0 must be the identity because t is always invertible. But I think, yeah, just to emphasize, the purpose of this is to emphasize that A0 equals identity. So, yeah, it's a one-to-one map. And the theorem is one parameter subgroup theorem. One parameter subgroup. Let A be a one parameter subgroup. Then there is a unique matrix X such that AT is equal to e to the tx. So one parameter subgroup always looks like this, e to the t times such a matrix. If you have a function like this, it's very easy to see that it satisfies all of these three conditions. So it is a one parameter subgroup. But the interesting fact is that every one parameter subgroup looks like this. So one parameter subgroup can be identified as just a matrix X because it's unique. Is everything okay? Section 2.5 is about polar decomposition of a matrix. But I will just skip it. You can just read the textbook if you are interested. And this is in the usually taught in linear algebra, so I will just skip it. And let me talk a little bit about chapter 3, Lie algebras. Finally, we can talk about the Lie algebras. We have talked about Lie groups or matrix Lie groups. So in this semester, we will focus more on Lie algebras. So, definitions and examples. So definition of a Lie algebra. So the last time I mentioned very vague description of a Lie algebra, but here is the correct or precise definition. A finite dimensional real or complex Lie algebra. So we can talk about real Lie algebra or complex Lie algebra is a finite dimensional real or complex vector space. So Lie algebra is a vector space, and denoted using this Gothic letter G. Together, together with a map, a bilinear map, denoted this bracket from G times G to itself. This is algebra, so we need to have a multiplication structure, and this gives us this, the multiplication structure, satisfying the following conditions. So it's a bilinear. Second, this is skew symmetric. So skew symmetric means xy is equal to minus yx. If you switch x and y, we get a minus sign. 3, this is the important thing. Jacobi identity holds. So what is the Jacobi identity? It's like this. X, y, z, and then you shift cyclically like this, y, z, x, z, x, y is 0 for all x, y, z in the Lie algebra. Then it's called Lie algebra, complex, or so complex means the complex vector space. Real means a real vector space. So you need to remember this. Jacobi. Easy to remember if you think of this as the cyclically shift. The 3 letters are cyclically shifted. Okay. But of course, there are different ways of writing this. Sometimes it will be written in a different way, but they are all equivalent. And we say that x and y in the Lie algebra commute. 2 elements commute if their bracket is 0. And we say that the Lie algebra G, we say that, so these are just the elements in G. We say that the Lie algebra G is commutative if every 2 elements commute for all xy in G. Yeah, so in fact, whenever you have a vector space, you can make it Lie algebra in a trivial way. Just define this to be 0, Lie bracket to be 0. Oh, by the way, this is usually called a Lie bracket or just bracket. So to define Lie algebra, you have to define the Lie bracket. How to define this? This should be mentioned. So if you define this Lie bracket to be 0, that is of course Lie algebra, and that's a commutative Lie algebra. But if you define this Lie bracket in a different way, you get a different Lie algebra. Notice that because of this second condition, the skew symmetric, we know that x comma x, or x bracket x, is always 0. Because if you switch this, it should be the same, but we have to have minus, so it should be 0 for all x. Yeah. So example. Oh, by the way, note Lie algebra is an algebra. Algebra means a vector space with a multiplication structure. Lie algebra is not associative in general. Associative means, associative usually means this, y, z equals, you can compute this first and then this later, or this, right? But this is not true, because we don't have that condition. We only have this Jacobi identity. So Jacobi identity is some kind of alternative of this associative condition. Instead of this, we have Jacobi identity. Example. This is a very well-known example. I guess you're all familiar with this. R3, so real vector space. Lie bracket xy for two vectors. Let's define this to be the cross product of, in the usual sense, the R3, the cross product. This is a Lie algebra. Proof is, just straightforward. You can check this. Notice, recall that R3 has three basis elements, and ij equals k, j cross k equals I, k cross I equals j, and using this, and you can check the Jacobi identity. And another example. Suppose that we have an associative algebra. So vector space with some multiplication, which is associative. And G is a subspace of A such that xy minus yx is in G for all xy. Suppose that we have a subspace, something like this, satisfying this condition. Then G with bracket defined to be this way, xy minus yx. If we define G with this bracket, then this G becomes a Lie algebra. This is a Lie algebra. It's a Lie algebra. Again, the proof is straightforward. You can just compute the Jacobi identity using this definition. And you can check that it is indeed the truth. In fact, interesting thing is that every Lie algebra arises in this way. For if you are given a Lie algebra, you can always find an associative algebra A, such that G is defined this way. Okay, we will see that later. So this is a very important example. And in fact, another example is GL. Let's use the next page. GLNC. This is the general linear algebra. As a set, this is exactly the same as this. But we want to give a bracket structure. And this is defined to be exactly as before. Then this is a Lie algebra under this bracket. This will be the standard Lie algebra for us in the sense that we will try to embed every Lie algebra inside this. And in fact, the embedding of a Lie algebra into this is just a representation of a Lie algebra. Okay, I think I should stop now. Thank you for your attention.